Asked to introduce myself this time. I guess who I am doesn't really matter. I'm just here to help spread some understanding. But my name is Thomas Hayes. I teach aerospace engineering here at OU. I've been in Oklahoma my whole life, going to different parts of the state. It's a pleasure to be here today to pass on whatever little I can about batteries, and I appreciate any other information you guys have from the audience. So as I'm talking about all this, I'll pass around kind of Peter Core's bucket of loose cells. It's just nice of him to provide that. Take note of the ratings on the cells. They give, of course, a milliamp hour rating, kind of a dimensional rating. And also really look close and look whether it's lithium ion, nickel metal hydride, or something else similar. These other packs of cells I'll pass around, and I've stripped one off independently. This is the kind of now a classic 18650 size standards, laptop battery, drill battery, etc., etc. Quite lightweight, especially in comparison to lead acid. I left one of these tab welded together because this is a battery that I've kind of stripped apart to make my own custom cell out of, pictured there and otherwise. But just again, have a feel of the size and weight, and pass those around if you've never really touched individual battery cells before. So the discussion about all this is if you want to go mobile with your radio, kind of the classic standard is to lug a big lead acid battery around, right? Or 4 or 5, your favorite 100-pound friends, you put them in the truck, and you get what you get. Well, I'll tell you what, this little handheld, easily portable battery is much, much, much more effective in my opinion for radio. I can run the radio about 4 to 5 hours off of this, fully discharge it, and obviously carry it around without an issue. I guess I'll go ahead and pass this around, but again, just kind of a piece of advice. If you have watches on or rings or something, that one should be safe. The other batteries that are open, you're already touching.
What's the chemistry on it?
This is lithium ion. Plenty more about that. I'm just getting those kind of out into the audience before we start discussing those in the presentation. But do be cautious around these batteries. It's one of the big things I'm going to mention. In fact, it's in the first slide. It's battery safety. So with these higher energy density chemistries, with these high power chemistries, lead acid is already kind of dangerous. If you've ever seen videos of people accidentally putting a wrench or accidentally shorting a lead acid battery out, it doesn't end well. The wrench, it basically welds itself to the terminals, heats up, and things start venting and exhausting fumes and things you don't really want to mess with. Well, lithium being much higher power means that it's kind of worse in that regard. Now, I don't think you're going to go out and drive your favorite nail intentionally into a battery. But just as a test, that's where this photo came from. An old battery was destroyed. And so if it shorts out, if the battery goes bad, if something's just not quite working out right with the chemistry, maybe it's just a production defect. Sometimes you do everything correct, but the battery has some sort of internal flaw, so the first charge or the fourth charge or the ninth charge, it just decides now it's time to expand, puff, and then rupture. Significant fire hazard, unfortunately, in the RC community, in other types of disciplines that use lithium batteries. People burn their cars down, their houses down, and basically anything else that can burn has probably been done at this point. There are risks. One of the easiest ways to avoid that risk is to just put them in what's known as kind of a LiPo bags. So to avoid this fire risk, if you're storing one, if you're transporting one in your car, if you think it's fine, and you want to be sure of that, put it inside of one of these. I call them specially designed, but if you're looking at the material they're made of, they're not all that unique. But it protects you and your belongings in your household if it does happen to rupture and something goes bad. All that being said, if you don't really feel up to the challenge of building your own, you always have the choice of buying some. One company that's really popular with mobile ham radio operation is Li-Lon. That's the battery shown up here in the top right. It's just like a fancy box, but inside is lithium iron phosphate battery chemistry. That's the chemistry basically to spoil my own presentation. That's what I recommend you go towards and use for ham radio operation for various reasons I'll justify. But off the shelf, Li-Lon for about $140, you can have a battery that'll run your radio 4 or 5 hours, easily picked up. What was it? Oh. Okay, you just pass it around. About $140, you run it for several hours, ready-made, much lower fire risk, has an onboard battery management system, several really good things that make this kind of a smart path, and many ham radio operators really enjoy battery from that company. In fact, I think even the mobile bicycle we have in the back room, that runs off a Li-Lon battery, right?
Yep, it's Li-Lon.
There we go. You can also buy them in more classic kind of car or UPS formats. So So you can kind of get the batteries in the shape that you want. To start with, we need to define what requirements you need to hit with a radio battery. This is the radio I use mobile. It's not maybe exactly designed for that, the way I use it, but hey, it works. 857D is what I started with an HF, and it wants 13.8 plus or minus 15%. That works out to about 15.9 volts and 11.7. So at maximum, if I want to eliminate all risk as posed by the manufacturer to burning this thing out, I need to stay below 15.9 volts, stay above 11.7 to keep the thing running. I did not do that successfully the first time I went mobile. Thankfully, I didn't kill the radio, but it had some issues. When looking at what battery you want to use, here's a different list of options. You can go all the way back to lead acid, which I was surprised to see is actually 1801 when lead acid was developed. It's kind of an old chemistry. Just made down this road yet? There we go. So I mean, it works. It's great. We still start most of our cars with them. It has its own risks. Don't forget about that. As we talk about the fire risk of lithium ion and all these other high energy density batteries. If you overcharge a lead acid battery, it discharges hydrogen. That can burn. That can explode. If you break a lead acid battery because it's heavy and you dropped it, you first break your foot. Secondly, you start spilling acid everywhere else. So there's kind of a weight risk as well. So older technology, then we skipped into nickel cadmium, which I'm sure some of you have some experience with, which is superseded almost every way by nickel metal. Twice the energy density of nickel cadmium, none of the memory issues. And so that brings you up now to the current year of 1967 when they first started developing and really researching nickel metal hydride batteries. 1980s, 1972, in fact, I think the team of 3 that researched the core of lithium technology just received the Nobel Prize, am I right? Somebody can, yeah, they just received it this past year, right? So thankfully they're finally honored for their work. And they did that development starting about 1972 and it's commercialized, about the 90s, really. It was a new thing in the 1990s when you were starting to use lithium ion cells in laptops and cameras and so on and so forth. Now, of course, it's commonplace. We're still making the better, still getting higher discharge batteries, now up to discharge rates of 100 times cell capacity, which is really, really, really powerful. These batteries will happily weld themselves to anything they can short through. So don't let that be your ring or your watch or your belt buckle. Fortunately, that has happened in Oklahoma. I haven't seen it, but let's just say something in Oklahoma State involving a rodeo, Wrangler's large belt buckle and a high discharge battery resulted in a sparking rodeo show in the battery room.
Makes you want to fire either.
No, definitely not. So what's interesting is among lithium polymer batteries, you have several different chemistries. You have cobalt, manganese, iron, and then now of course lithium sulfur kind of on the horizon being developed as much lower discharge rate battery, but hey, it'll get there eventually for radio use. In fact, if you want a large battery, it'd be just fine already. The most common, I would say, is probably lithium ion, lithium polymer. Those cells are used widely in RC airplanes, drones, laptops principally use lithium ion 18650 cells, as do your power tools. If they say lithium powered, that's probably what's inside this battery pack. By 18650s, I mean those round cells that just passed around. A very, very common standard. In fact, there's a whole market, kind of a secondary market that exists about taking broken and dead laptop packs or electronics packs, stripping out the cells that are still good inside of them, and reselling them on the market at a much reduced cost, because it might only be 1 or 2 cells that have gone bad and ruined the entire battery pack. It's a lot of work to go replace that by itself, but hey, if you're in the market of taking them out, reselling them, that exists, and it thankfully lets you, if you want to fabric cobble your own radio battery, get some very, very cheap, still very capable cells. So it's interesting to see there's different lithium chemistries, different developments. And what's neat, polymer, manganese, and iron have roughly the same energy density, roughly. There's some variance, but it's not huge. Lithium sulfur then doubles it again. So compared to lithium polymer, lithium ion, lithium sulfur chemistry, per pound holds again twice as much energy. It's in research, it's in development. I would not call it mainstream yet, but very long endurance UAVs, very long high altitude solar aircraft are using them already. So if you hear about records being broken of 2-week flights and 2-month flights in UAS, that's the battery chemistry they're using, lithium sulfur. It's really, really impressive, but they need to work some of the problems out for higher discharge operation. To weigh the difference between cost, weight, and lifespan, that's really if you're looking at this from a financial perspective. Seeing how long If you spend a bunch of money on this battery pack, I'm going to be able to use it 10 times, 100 times, 500 times. Is it going to weigh 400 pounds? Can I even carry this with my hands? Who knows? So lead acid, you're going to be between 80 and 100 bucks per kilowatt hour. We kind of know what lead acid batteries cost. You can probably take an older one out of your vehicle if need be, if it still has any usable life in it. If it's not very good for your vehicle, it may not be very good for your radio. But lithium-ion cells, even though they're much more expensive, so 3-4 times the cost per kilowatt hour of energy, they will last longer. They deliver more usable power to your radio system because lead acid starts to sag. They have much higher internal resistance, which we'll touch on here in a bit. And the nice thing is they're smaller and lighter for the exact same capacity. Of course, all these charts in the presentations are taken off, hopefully, the websites that I've linked as references. But you can really see this top right-hand chart here that lead acid has the worst volumetric and the worst gravimetric energy density of all these different batteries that are available. They are cheap. You can go to the store and buy one that has big ratings on it. It's not going to cost you a whole lot, but in the long-term perspective, it might cost you more than you're thinking. If you want to buy a battery that you're going to have for years and years, to run your radio for a long period of time and be easily portable, especially if you're going to go hiking or something similar, it's probably worth going ahead and investing in some lithium-type technology. Even from a cost perspective in kilowatt hours per dollar, once you look at the total life cycle cost, it's really comparable, if not better, to buy the lithium batteries. So these are just some charts from manufacturer specs showing that with a discharge depth of only 50%, lead acid battery is only going to last about 400 to 600 cycles. That'd be 50% depth of discharge using half the battery. That's probably standard for radio operation for several reasons. One of these reasons we can start to fill in the story and develop things is looking at the voltage that each individual cell offers inside of a battery. So you might be looking first at lead acid and say, like, wait a second, my lead acid battery makes 12 volts. It's not 2.1. Well, your lead acid battery in your car actually has 6 independent cells in it. It's a 6S1P battery. So each individual cell in your lead acid battery has 2.1 volts associated with it. Fully charged, if you're like have it running on the alternator, if you have it running on a charger, they should cut it off somewhere, depending on the exact type, whether it's absorbed/NAT or some other type of cell. Should be somewhere max around 2.4 volts per cell. Yeah.
Can you just back up just a bit and explain that terminology, 6S1P, please?
Okay.
Oh, are you going to get to it?
I'm going to get to it, but
then that's fine.
Are you sure?
Yeah.
Okay. Apparently it's farther forward than I thought it was, but suffice to say, 6 of these cells in series are connected inside of the normal, plastic housing car battery. And we start looking at making our battery packs. You can now choose how many to run in series, how many to run in parallel. But when you deplete the lead acid battery, you're down about 1.5 volts per cell, and that's when it's dead. It's going to be at the end of its capacity, and the voltage is really going to drop off near instantaneously past that. Nickel metal hydride. We've heard these being called like the 1.2 volt batteries. It's kind of like if they're non-rechargeable, you get a battery that's 1.5 volt AA. If it's a rechargeable AA, it's going to be 1.2. That's the average voltage. When you fully charge a nickel metal hydride battery, it's 1.4. When you fully discharge it, it's 0.9. And I promise there's a good reason I'm going over these specific cell voltages, because we're going to have to make decisions on how to structure the battery pack so that it fits the voltage range of our radios and doesn't cause electrical issues. Too much voltage, too little voltage. Either one is bad for different reasons. Now, lithium polymer and lithium iron, even though they're both lithium chemistries, lithium polymer is an average of 3.7, lithium iron is lower at 3.2, which sounds like a bad thing, but it's not. It's actually really, really good for our purpose. Because lithium polymer, LiPo, lipos is what people call them, peaks out about 4.2. So when you pull it off the charger and it's full, quote unquote full, when your phone is full, each individual cell in your phone or your laptop or your RC airplane or your radio battery has 4.2 volts. So that means if you have one cell, it's going to be 4.2 volt battery, 2 cells, it's going to be at 8.4, 3 cells, doing live math, hope I don't get it wrong, 12.6?
Yep.
All right, good. God, I can multiply today. It's a Saturday. I don't want to do math on
Wait a minute, you build airplanes?
Well,
There's an app for that.
Oh,
exactly. On the computer. So the depleted voltage now, you get down to about 3 volts. So you see there's actually a wide range these batteries are going to go through. Now with lithium iron, one thing is a trait of that battery chemistry is they don't go through such a wide variance in voltage, in cell voltage. So the average voltage is 3.2. You see there's not as large of a difference between the peak and the empty. In fact, empty for lithium iron, I would more appropriately call that 3 volts. 2.5 is kind of over discharging lithium iron, and plus you're not getting much extra energy as you pass from 3 volts to 2.5. The voltage is dropping really quick, and you can see that when we look at discharge curves of various batteries. So this starts with the oldest technology, lead acid, but it's also the cheapest. I mean, I'm sure most of us have used a lead acid battery to power a radio. If not that, it's obviously probably sitting in your car. We hit them with massive loads when we start our vehicles. Hundreds of amps, right? You hear them rated in cold cranking amps and other kinds of ratings like that. Seldom do they rate these batteries in amp hour capacity. They don't put a label on there and say, this is a 30 amp hour battery. I tried to look that up, and so few manufacturers will actually say or give you any rated capacity that you're kind of out of luck. Now, the solar markets, like the battery backup for solar plants, wind plants, they do a better job of getting actual ratings for capacity of lead acid batteries. But your automobile, marine batteries, RV batteries, it's hit or miss. That being said, if you were looking at not to hit them with a large draw and then let it recharge off an alternator the rest of the time you drive, if you're actually going to use this for kind of a steady discharge, low-ish current for a long period of time, you now need to understand what this C term means. And that's a C rating of discharge. That's a way of looking at this in kind of a non-dimensional form. So as the battery gets bigger, its ability to discharge energy grows as well. That's the number of times the battery's capacity in discharge that you're hitting. So the note I looked at and put up there, so I remember to tell you, is a Group 27 lead acid battery has roughly somewhere around 85 amp hours of capacity. That'll vary with the brand, that'll vary with temperature, that'll vary with how much load you're pulling out of it. But that's roughly what you're looking at. So 1C discharge from an 85 amp hour battery would be 85 amps. And I hope your radio is not pulling that. Maybe it is if you have your amplifier and your radio and everything else.
85 amps for 1 hour.
No, actually, 1C is just the discharge rate in amps. It's not necessarily an amp hour rating. I think it's just amps discharge. I think.
No, it has to have a time.
For energy.
So it's current.
It's current, though. It's output current is how they rate
Right.
these. So these are curves of varying current discharge.
Okay.
So a 1C discharge, which would be the curve here, that's pulling 85 amps. So if we're pulling, my radio again pulls about 22 in the manual that I put up. So that'd be about a quarter C. So we're looking about here-ish. So if I was actually transmitting constantly, be on the 0.2 C line. If I was just running the radio, which is resting current draw, I think it's about 1.5 amps, you're way up there on the 0.05. What you should realize is that the voltage is pulled down substantially as you go to higher and higher current draws. It's due to several reasons, internal resistance being one of them, which we'll cover in an upcoming slide. But also just the heating of the battery affects the chemistry of the discharge state. Look at the shape, though, of lead acid. It starts off very flat when it's fully charged. It holds that voltage for some period of time, then it drops off substantially. So does this happen to have a laser on it?
Yep. Big one in the middle.
Big one in the middle. Not going to miss it. So what you should really, and I have a problem with, once you get to about half of your discharge energy, the voltage starts drooping and will cause problems for radios. Nickel metal, that was the next, what you might call improvement over lead acid. NiCad was actually kind of the intermediate step. The nickel metal supersedes that. This is something that we've had some pretty good experience testing at the university, and forget the scales at a different unit now, I didn't make this chart, but that's actually in millivolts, so that's 1.4 volts, not 1,300 volts, that'd be one heck of a battery. But, so it starts at 1.4, and very quickly, once you run this for just a few minutes, sometimes it's only seconds, it burns the peak of the battery off. So that might only be a couple minutes, just a few seconds, and then you're down to this, what you might call the standard-ish voltage of 1.2. So it spends most of its discharge curve somewhere in this region, as you can see, but as you start depleting the battery, it runs steeper and steeper and steeper as it's depleted. So nickel metals work, but this, again, is kind of throwing some water on the idea that batteries have a constant-ish voltage. When you buy a 1.2 volt battery, it's not really 1.2 the entire time. It starts a bit higher and ends a bit lower. We need to be aware of that to protect the radios. Moving forward with LiPos, similar shape, much lower internal resistance, but they start fully charged at about 4.2. Now the reason there are multiple curves is because these are now different amp discharges. So a 25C discharge for this type of lithium polymer battery is about 42 amps, which by the way, 25C is kind of sleepy for modern LiPos, which is impressive if you look at what the capabilities of nickel metals and some of the older battery tech can do for a long period of time. Be respectful, and I tell my students to be very respectful of the power LiPos can source if they short. So it means fuses everywhere, protect yourself, and take off your big metal rodeo belt buckles as you're working on these. So, as you can see, as you discharge them at higher and higher levels, up to 68 amps, now 40 C from this battery being tested, but of course I just took this from some manufacturer's website, is down appreciably lower in voltage because of internal resistance and other heating effects, but it's still relatively the same shape. So again, the story being told here is that you burn off the peak voltage in the first few minutes, the first bit of capacity. You spend most of your time in this somewhat flatter, almost constant range until the battery is what I would call mostly depleted and you fall off the cliff. Now, the target battery. This is what I'm just going to flat tell you. If I could build any radio battery I wanted, we do lithium ion. One of the big reasons is look how much flatter lithium iron's discharge curve is than lithium ion. That's a property of the chemistry. I'm not a chemist. I can't explain that part to you. But I can show you the chart and say, hey, it's true. You start about 325, hit the end, and of course it falls off a cliff like most other batteries, but it has a very consistent, very constant discharge curve. That makes them very, very useful. And again, you see various curves for different loadings, going all the way up here to, I guess, 3 amps. It's a much lighter loading, though lithium iron can certainly power much higher currents. In fact, some colleagues and friends, one of them was into Mazda racing, Miata racing, and they actually replaced the big, heavy lead-acid battery in their car with like a little tiny lithium iron battery to start. Saves weight, goes faster on the racetrack, right? So it worked wonderfully. I actually had a student using one of our, they told me this after, but using one of the small airplane battery packs we have, small, relatively small airplane battery pack. Their car died. They left the lights on when they were out of the field test flying, everybody else left. They started their car off our airplane pack and left. Works. Little tiny batteries start automobiles very easily with this technology. So now, we're at the description of S and P. Now you have some knowledge about different chemistries that are out there. You still buy all the cells I've listed. You know the kind of the discharge curve profiles. How are you going to put it together? You could have 10 cells in series and 1 in parallel. With nickel metal, 10 in series, since they're 1.2-ish average per cell, gives you a 12-volt battery on average. Peak would be higher, 1.4 volts times 10. I guess that's 14 if I can do that hard math. And then when it's depleted, it'd be about 9 volts per cell. If you do the same thing with lithium polymer, and it's 10S, well now because each individual cell's voltage is higher, you're going to be at a 37-volt battery whenever it's just resting in normal. So that doesn't make much sense. But this is basically just the lingo, the phrasing used to describe configurations of batteries as we start to stack these Lego blocks together in different, connected orientations, different connection schemes. If, like in this example down here, you have, in this case, it's 6 batteries wired in parallel. So all the similar poles are connected, actually tab welded, which I think you're going to speak to in a little bit. In fact, this is a tab welding machine right here that I think you're going to hear a bit more about. Tab welded, in fact, if you look at the cells that are passed around, you'll see the welding marks where they've actually been not soldered, not glued, I don't know what kind of glue you use, but actually weld the little tabs to it. You weld them in parallel. There's a series connection to the opposite pole, and the thing you're not seeing is on the bottom. There are tabs here connecting the middle 2 rows. So 6 wired in parallel, series, so 4S. This pack would be described as a 4S6P lithium polymer battery.
Tim.
Oh, yeah, take a look at those. You look for the little spots, the little dots, and just any other kind of spot welding, so it's done at a very small scale. The top one, which is a different type of battery, but still the same chemistry, it's just called a prismatic cell instead of a cylindrical cell, where these internally, if you chop one open, please don't, they make fire. It would look like a Swiss roll. This would look like lasagna, but they've laid all the layers flat. So cathode, anode, or electrolyte just layered up appropriately to form the battery. So that would be a 2S1P. In fact, oftentimes just called 2S because the 1P is just understood. You've done no parallelization of lithium cells. In fact, these prismatic cells get so big that unless you have really good reason, it's usually not parallelized at all. You can get 10,000 milliamp hour prismatic cells quite simply. Just go to any drone website, you get what you need. And then now we look at what all this information has kind of been building up towards. One of the steps, there's still a few more steps involved. As you have all these options of chemistries, you have all of these options of individual cell voltages and how many to wire in series, what's the right answer? The green range is what the radio wants. So if you are too high, as would be the case with a 5S lithium polymer cell, you're going to start off in excess of 20 volts. Your radio probably won't survive that. It probably would not work.
KX3 says anything over 15 volts voids their warranty.
KX3, okay. Well, yeah, I referenced my radio specs, so I want to stay within that for sure. The only one that stays completely within the range, you would think lead acid would. It starts there, so thankfully it's not going to burn it out, but as you deplete the lead acid battery, remember that discharge curve I showed? By the way, these slides are going to be probably up on somewhere. You can go back through
On
and
the
reference
battery
it.
page, yep.
Sure. This is why lead acid, you can't really use the bottom part of the discharge. Once the battery discharges about 50%, your radio might very well just turn off, or you might be browning it out, doing some other sort of more complex electronic effect that I can't really comment on. However, the one that falls entirely within the range due to its very narrow discharge curve is a 4S lithium iron. That is why a lot of radio batteries that are constructed, a lot of radio batteries that are sold are exactly that, a 4S lithium iron pack. Yes?
But you'd have to have some kind of electronics to make sure it doesn't discharge past the bottom.
Got a slide coming on that.
of the cell.
For the lithium iron? Actually, for any of the lithium cells, yeah, you don't want to over discharge them because that'll ruin the chemistry, it kills the cells.
Left your radio on and it's powered portable, and when you go to lunch or something that drops down below, you could have a fire or something.
Absolutely, and the easiest way to do that is called a BMS. They're about 10 to 15 bucks. We wire one in, we'll have a slide coming up with that here in a bit. But yeah, you're absolutely right. You don't want to do that. I don't know if it necessarily causes the cell to rupture, but it certainly destroys the chemistry, won't charge correctly, and then at that point, it could pop and burn, potentially. I may have ruined more than 1 or 2 lipos that way. Happens. No fires yet, thankfully. But this just shows with all the different choices of different connections to the series, like a 10S, 11S, 12S nickel metal, and 3S, 4S, 5S lipo, that's why I'm saying you should build a 4S lithium iron pack. Speaking of voltage regulation, I tried the top option. It was a cheap voltage regulator, so it can handle anywhere from 8 to 40 volts input. Output's 13.8, so right square in the ideal range for my radio. So that way I actually did this with a solar setup, so I didn't have to worry as much about voltage fluctuations, the effects on my radio. And hey, yeah, it worked. Okay, so it put out 13.8 volts. You hook up a multimeter to it, 13.8, thanks. Turn on your radio, can't hear anything. It's a switching mode power regulator. So instead of using linear regulation, where it's just discharging currents, burning off the excess, that's inefficient, but it won't make noise, this switching mode regulator basically became like a cheap wall wart. We've heard the stories of those polluting kind of RF, and if it's close to your radio, you're going to hear it through your antenna, and it just drowned out everything I actually wanted to do. So not that great for radio use. The second option, MFJ's box. This one, reportedly, haven't bought it, haven't used it, but it's reportedly radio quiet, as you'd hope from companies selling radio equipment. It will take something from about 9 point whatever volts to 13.8 and boost it to a voltage you tune somewhere between about 11 and 13.8 volts. Notice when I said boost, it won't take higher voltage, as you would get with lithium, and reduce it down to the target range. It will only take something that is low and boost it up. And they sell this principally for large banks of lead acid batteries, which have no problem on the top end, but discharge too far. That box lets you take cheaper lead acid batteries and use all of the capacity instead of just half-ish of it to run your radio safely. Now, it still doesn't really make it all that cost-effective to buy lead acid because, yeah, your batteries are cheaper, but now you have to buy a $170 box to use all of it. So why not just spend a little bit more on the battery, and with the better battery, fewer systems to take care of. It's just from a total cost perspective, lithium still is pulling ahead, at least for small battery backups. Yes?
Also for cycle life, for lithium iron phosphate has a cycle life of about 2,000 cycles.
Yeah.
Lead acid is about 200 to 300, and lithium iron the iron polymer 3.7 volt cells, they're only about maybe 500 to maybe 800. So lithium iron phosphate is actually the cheapest, no matter how you look at it,
Absolutely. I mean,
with the best regulation.
when you buy a lead acid battery and you're going to use it for years, you're going to be buying that battery 4 or 5 times before you'll have to rebuy the lithium battery once.
And they're getting pretty expensive too now.
They can be, yeah. Well, the way I actually chose to regulate my battery pack is this little guy here, which I'll toss around, we can pass it around, but it is a diode, right? So diodes create a relatively constant-ish voltage drop. Notice this is a logarithmic scale. So if you're pulling between 1-ish amp and 22 amps, which would be that second line there, you're going to drop between about 0.7-ish volts and we're up here, 1.1 or so volts out of the loop. So that's a fairly constant, better than you get with a resistor type of voltage drop. Yes, you are burning the energy off, but it fixes the problem of me using this type of cell chemistry. Whenever I'm up here at the 4.2-ish, 4.1 range, at the peak, just off the charger, fully charged battery, I throw that in line with the battery connection. I should remember to if I forget, that's a problem, right? And it knocks a volt off, making it safe to turn my battery on. Once I can see in the radio's voltage readout that, okay, I'm off peak, I've depleted enough power, just turn it off for a few seconds, pull that out of line, plug everything back in normally, and my battery's not going to overvolt the radio anymore. That's a workaround? Yep. But the nice thing is, instead of $170 for the MFJ box, I spent about $1 on that. So it's very, very cheap, very high power capability, handles about 50 amps, only using one channel of the bridge rectifier, so works out quite nicely. Now, it doesn't work at all if I forget. Yes?
Right, and so what happens at the other end when you get down to the bottom?
It's already out of circuit.
No, if you forget.
If I forget, then my radio turns off early.
Okay.
I've had that happen with lead acid. In fact, that story's coming up on a future slide where I was operating off of a smallish lead acid battery, and whenever I tried to transmit the current draw, drop the voltage, shut off the radio. When I let loose, the battery would recover, and then the radio came back on 10, 20 seconds later. We'll get to that though. But this is a nice way to very cheaply and without RF noise burn off about a volt. Yes, you're wasting it. Yes, that gets a little bit hot, but they make heat sinks and things you can put onto them very cheaply. It's never become so hot that I've been worried about it in kind of standard radio operation. So we talked a bit about this and hinted at it because there's still one more complicating factor. That as you load up batteries, their capacity and their performance reduces. You've seen this in the charts, you've seen those in the voltage profiles, that as you drew a higher C rating out of each individual battery, its performance degraded. So here you can see as you draw 0.2 C, you get great performance out of the battery. Starts off at peak voltage, you get maximum capacity, and you get 100% of its rating. That's not always true. Manufacturers aren't always telling you the truth with their fancy labels. Surprise, surprise. But as you pull more and more current as a percentage of the battery's rating out of the battery, so if it's a 1,000 milliamp hour battery and you're pulling 2 amps, that'd be 2 C. 1 amp would be 1 C for a 1,000 milliamp hour battery, so on and so forth. That depletes not only it pushes down the voltage, yes, but it's also depleting the actual energy output from the cell. You're losing stuff chemically. Ratings go as high as 70 to 100 C for some lithium ion types. Those are really high performance drone batteries, UAV batteries, just scary powerful. It's to the point now where battery powered vehicles are outrunning gasoline powered vehicles and reciprocating motors. There's a tremendous amount of power available from these systems. But really the story that's being told here is one of internal resistance. And this is another giant difference between lead acid. I've already hinted at this. You probably heard a few terms in the rest of the discussion, but lead acid has appreciable internal resistance. Meaning that the battery is not just some magic voltage source. It's not just 12 volts sitting there and it's going to discharge to whatever else. All batteries contain some series resistance inside of themselves. This can be the only thing keeping you safe with some cheaper batteries. Like a AA, you don't worry about shocking yourself. It's 1.2 volts, but even if you short them, it's not that big of a deal. They have appreciably high internal resistance for most consumer cells. Lead acid batteries, in fact, here's the story I was speaking of. This was my first mobile battery. Not exactly that, but you get the idea. It was a little mobile jump start pack. I'll just take it out, throw it in my passenger seat, plug the radio up to it, just with jumper cables. Said, hey, cool, I'm going to go do mobile radio. 15 minutes in, radio just switches off. It had been working fine, okay, 12 volts, it's just like a car battery. If this can jump start my car, I can certainly run this little radio. No big deal, right? Well, under load, 22 amp load from the radio, at 100 watt transmit, the internal resistance of these, especially smaller batteries, this is not a full-size car battery, of course, can be 0.2 ohms all the way up to about 1 or 2 ohms. So pulling 22 amps, that suddenly takes off multiple volts from the stack. So it undervolted the radio switched off. Of course, didn't know exactly what happened the first time I was messing around. It was like, oh yeah, dummy, internal resistance, lead acid battery is pretty high. This is a cheap lead acid battery at that. It's a small lead acid battery, you can count it even further. And so I got a whole 15 minutes of radio time. That's combined transmitting and waiting and listening. Not a great option. Looking at and comparing this to lithium cells. So lead acid, they're about 0.2 to 1 ohm and higher, depending on what cell you're using and so on and so forth. Nickel metal, pretty good, 15 milliohms, much better battery technology, can handle much higher current draw. Still, but somewhat appreciable voltage loss. Lithium now is just getting obscenely small losses to where your connections to the battery might have more resistance than the actual battery has internally. So be careful with how you connect to it. This is the story that caused my first mobile op to not really work. The lead acid at full current created a 4.4 volt drop. So what started at 12.5-ish volts, runs my radio fine. Whenever I click the transmit key, drop down to 8. Radio turns off, no more fun. When I go off a lithium battery that's fully charged, I'm pulling 22 amps from that handheld battery, wherever it's gone off to, enjoy your new battery. Only 0.66 volts drop under the same load. That's the reason internal resistance matters. That's another feather in the cap of these lithium technologies, is that they can source a bunch of current. They don't lose capacity while doing it, and they don't lose voltage either, so your systems connected to it are not as negatively affected by pulling these current draws. You can use all the battery capacity that you see in the plot at high current as well, which 22 amps from a small battery is fairly high current, right? It certainly beats a flashlight. So bringing this to the other discussion of charging. So at this point, that's kind of the full story that I can tell you today about discharge and types of cells and capacity. But if you're going to own one of these, you need to know how to charge them safely. If you use the wrong type of charger for a lithium cell, it's going to be a really bad time. You're going to waste a lot of money, maybe start a fire. So charge it appropriately. If you're charging nickel metal cells, if you're charging lead acid cells, they usually just apply a voltage and you kind of either trickle charge it or power charge it. And it kind of sets a voltage and waits for the battery to come up to that. It's fairly simplistic charging. Just a constant voltage type regulated system. If you're charging a lithium cell, it's simple for the first part. You charge at constant current for the first 60, 70% of the cell. It varies with what charger you use and what battery profile you're charging with. But once you finish that constant current mode, the charging voltage to maintain constant current would actually exceed the maximum for the battery. So they switch logic at some point during the battery's charging cycle, usually 60 to 70%, to constant voltage. And so that voltage will be held constant at 4.2 volts. You see the charging current drops off kind of exponentially as you approach full. This is why your cell phone charges really fast from nothing to 70-ish%. This seems to slow down the closer you get to full. This lithium ion, lithium iron, lithium technology cells have to be charged that way or else you're going to have a problem. So this is, you need to use a charger that uses and has that type of logic. Thankfully they're not that expensive. In fact, you can buy these hobby chargers with touch screen interface, color screens, all sorts of different connections, balancing properties for less than I probably paid for my automobile battery maintainer charger. This is $8. Touchscreen, color. It charges lead acid, nickel metal. What? $80. 80. Yeah, pretty cheap, pretty great. We
420s.
420.
$420 bills.
420 is something different.
But lithium ion, lithium polymer, lithium iron, lithium high voltage, which I haven't really talked about in this lecture much. It's a little bit different. Suffice to say, it has many different storage charge profiles, can charge what you want when you want it, different sizes of batteries, etc. Yes.
Is that stroking back what the hoverboard people were not doing on the lithiums and just overcharging them? That from going from constant current to voltage?
There were several issues with that. I think one of which was cell quality. Sometimes they just have a bad cell and they weren't ever really feeding out cell balancing. Another issue is, of course, they might have just been overcharging, they plug in the wrong type of charger. There's several reasons those hoverboards were lighting off. But I haven't gone super deep into that history. I haven't never owned one. But suffice to say, this is what I recommend for a charger. I have quite literally recharged my trucks multiple times using my hobby chargers. They just work. Charging is charging for lead acid batteries. This is where we're kind of speaking to. So now, one of the things you have to be careful with if you're going to be using lithium iron or lead acid, or not lead, lithium technologies of any type, is you really need to keep the cells in balance. What that means is if it's a 4S pack, meaning 4 cells in series, you want each of those cells to have roughly the same voltage. You don't want one to be sitting at 4.2 volts, 4.2 volts, 3.8, 4.2. That would cause an imbalance. As you charge them, the 4.2 cells will get full. 3.8 still wanting more as the charger waits for the total voltage to come up. You're overcharging 3 of your cells while the last one reaches where it should be. So you're damaging the packs. What most of these advanced chargers, you see link here, here, they have individual cell taps. That's what all these individual wires are. They have different sizes. Like the 8-pin, I think would be for a 7S battery, 9-pin, 8S, etc. You plug that into your charger, and it's actually reading and monitoring every individual cell voltage. Now those wires aren't very big, it's not putting a lot of power in or out through them, but it helps to keep them balanced by putting a small load as you're charging that balances those cells back to level, keeping things safe. In one discharge and charge cycle, it'd be very hard, unless your cell is damaged or just bad and defective to begin with, to get things so out of balance that it's just not going to work. But over the course of 10 charges, 20 charges, if you don't balance charge, if you don't ever put a balancing unit on the battery, you could have some serious issues resulting in massive battery life degradation, popping, fires, it could go bad. So make sure you use battery balancing of some measure. Now to go through the kind of simple steps of making your own, I would stress that keep things safe, don't use a metal work table. Had some students try to sit down at one of those and have to correct them.
Balancing pin on that.
There's another way around that. You're right, because I didn't have a balancing set of leads coming off my battery, and there's another way, which I'm coming up to. Know that even if you have everything, I've soldered before, I've done battery connections before, it still took me way longer than I thought to make this thing. I thought I'd sit down, a couple hours, no big deal, just make some connections. Now I get pretty cautious whenever I'm messing with these batteries, so it took me about 6+ hours to put this thing together. It ended up being kind of a whole Saturday. It was fun, I was glad it was over, but still surprised still at how long it took to assemble these. So as you're considering the build-buy trade-off, just consider how much your time's worth. You start with cell holders. You can either buy 10 of them-ish for $5 online, or if you have 3D printers, that is a link or a readout from Thingiverse so you can print your own. Printing your own, of course, you get the configuration you want. You don't have to worry about what's just available elsewhere. But you start with mechanical holding because if there's just a loose connection of cells, it's going to be hard to assemble everything else. This is what's hiding inside of my battery pack. In fact, I guess it's there in the back, but you probably felt there's a lump in the middle side of it. In fact, nope, obscured there underneath my tape. But the battery management system is where the cell balancing happens. I actually have a board that lives with that battery pack dedicated to it. It costs about $10, $15, and you can buy them specific to your battery chemistry. Maybe if you have lithium ion cells, you want to buy a lithium ion BMS, battery management system. If you have lithium iron, you want to buy a lithium iron BMS, because that has the voltage levels and the charge-discharge profiles built into them. It knows the upper and the lower limits. I think some other gentleman mentioned that you don't want to over-discharge them. Yeah, this...
Why would you do that if you could just put a pin on it and charge it with an external charger?
Put a what?
Why would you use that board,
BMS?
balancing board, rather than just use a pin?
It does add a little bit of safety. You're right. If you're competent and you're never going to over-discharge it, you're never going to overcharge it, and you just use one of these external chargers, absolutely you don't have to have this. You don't. But I think in the circumstance somebody suggested earlier that maybe you fall asleep or maybe you get lunch, forget to have your radio on. Yeah, this will shut everything off, noticing that your load is connected to a different connection than the charger. It has logic in between those. If it knows you're on a 4S lithium ion, it will disconnect the whole thing with solid state methods before you damage your cells. If you're charging it and you leave it on the charger too long, you connect the wrong type of charger, it disconnects the charger from the batteries again. So this is kind of the safety logic protecting yourself from yourself. And I like having that because I do stupid things. So noticing here as well, it has the balancing connectors internal. So now when I charge these cells, technically all I have to do is just plug it in to the correct voltage source. This handles all/most of the charging logic, and it handles this cell balancing its entire life. It has one of those little logic controllers in there, and its entire purpose in life is just like, are you at the right voltage? Are you at the right voltage? Are you at the right voltage? Hundreds of times a second, that's all it does for a living.
What is the name of this thing that you got?
This?
Yeah, where would we get that thing?
I got it off eBay. $15 battery management systems. I'm sure there's a wide variance in quality.
What's the name, what do you call it when you look it up on
BMS, battery management system. So BMS board.
Links where we put the,
Sure.
what we put the slides, we put links for all the various things.
Now, yeah, go ahead, question.
You talked about cells in series
Yes.
and the problems. What about cells in parallel?
Ah.
That's also a problem.
Absolutely, absolutely. In fact, I have a slide coming right there. So we'll talk about that. And you notice I even copied and change this graphic up myself because this starts to indicate how I wired the battery pack that I handed around. It's a 4S6P. I wasn't really satisfied with the capacity of one of those 18650 cells. I think mine that I got cheaply were only like 1500 milliamp hour per cell. 18650s hold reliably up to maybe 3000, 3400. Above that, your manufacturer's lying to you probably. But I wanted more capacity to run the radio longer. It's, you know, it's still going to be plenty light enough. So I started doing these in parallel, and there are some risks. You're right. Before I get to those risks, one other thing to keep in mind is the gauge of wire you want to use. If you're going to be pulling 20 amps, if you bring your amplifier with you, you're going to be pulling 150 amps, be sure to use the right wire gauge. Not only do you reduce fire risk, but consider that the wire itself creates voltage drop. You've gone through all this trouble to reduce voltage drop with the lithium cells. Don't put small, high resistance wires between the battery and the radio, and just waste that power elsewhere. So put this in here for your consultation. This is the table, part of the table I send for my students to reference, and you can use different circular mil per amp, basically different current density ratings based on how you want to run your own show. CM/A is circular mils per amp, so higher numbers means more current, more heating. The 60 to 75 is probably what I'd recommend you staying at for radio use. But for the most part, 20 amps, we more or less manage that. So here's the risk of parallelization. You're right, you're absolutely right. For example, my battery would be 6P. This is a 5 parallel diagram, meaning that, okay, you have these lithium cells are fully charged, 4.2 volts apiece, but instead of having just one of them, so you have 4 cells stacked in series, I think of that as like vertical voltage or building up vertical pressure, if you will. You start putting a bunch of parallel. So 4.2, 4.2, 4.2, 4.2. You don't get additive voltage, but you do essentially increase the capacity of your battery. So if each one of these was 1.5 amp hours, you have 1.5, 3, 4.5, 6, 7.5. So you actually increase the capacity of your battery by stacking in parallel. Sounds good, sounds great, as long as everything works nicely, you're good to go. But let's say you drop it. Let's say you get some sort of, just say you drop a hammer or a pike, or you damage one of these cells. Say cell number 4 here, and it maybe has an internal short, or maybe its chemistry has gone bad, just had a defect or something. What happens when one of these batteries goes bad is that it is now connected, it makes its own circuit out of balance with the other cells in parallel. So all these other healthy cells at 4.2 volts have a very low resistance connection into Mr. Damaged cell and flood it with current. If it's damaged, it's not really going to even charge up. Sometimes they do successfully equalize, and you never know this happened. And it's not really ever manifested into a problem. But sometimes it becomes bad enough that the pack will rupture inexplicably. One company that has kind of solved this is depicted here in the top right, is Tesla. It was weird. I saw a close-up in a different, totally unrelated video I was watching of these batteries, and those little wires, now keep in mind, there are hundreds, if not thousands of these cells in a Tesla, Model S, whatever, car pack. Pull all the current, all the energy necessary through little tiny wires that serve as fuses. So if one of these cells goes bad, and the rest of the battery track tries to flood into it because it's just shorted to 0 or very low voltage, that wire melts, problem solved. And the rest of the battery, yeah, it's a little bit out of balance now, but they're so highly parallelized in those battery packs, it doesn't really matter. It's good to go.
Yeah.
Yes.
Yeah, the Tesla Model S has like over 7,000 18650s in it.
Wow. That's a
Yeah,
lot.
and now they have a newer cell, the 21700. It's a little bit larger in diameter and taller. It's got like 40% more capacity, so it's more
They're certainly
capacity.
experts in batteries, as you would hope.
Yeah, so the Model 3 uses the new larger cell.
Yeah. Well, it's pretty, I just thought it was interesting that all the current to drive a car comes through little tiny fuse wires. It's just each individual cell is pulling so little because it's just a large team working in connection.
Is Tesla the only one that uses it?
That's the only example I know of, but I assume other battery types use a similar strategy. So, kind of drawing things up to a close, passing on some favorite toys of mine. This is a very cheap toy for charging. If you're like me and you have airplane batteries and radio batteries and car batteries and this battery and other batteries, and you have one charger, this is something very cheap to buy. I think it's 10, 15 bucks, and I just call it a squid. Because it comes with all these connectors wired on, they're all in parallel, so if you shouldn't plug in multiple things at once, but if you have some power poles and XT60s and who knows what the rest of the stuff is, you've got the connection you need. Worth the money, absolutely want to let you guys know about it. To go on to more specifics of how to make a battery, how to wire things specifically, aside from using the wonderful diagrams here contained inside your eBay BMS. That was the extent of the documentation, by the way. There's no other PDF. Yeah.
Oh, one thing with the BMSs, all of them, like for lithium ion, ION chemistry, they're all 4.2 volts, and I was trying to find one that you could adjust, say down to 4 volts. If you bring, for every 0.1 volts in lithium ion, ION chemistry, you go down, no, for instead of 4.2, if you go down up to 4.1 volts max,
Yeah.
you double the cycle life. If you go to 4 volts, you quadruple the cycle life.
That's absolutely true. If you don't go through full cycles, if you don't fully charge, these batteries last a lot longer. There's several, what you might call tricks to extending your battery life if you're really concerned about maximizing that.
Yeah,
Certainly the Teslas even do that. They give you, their onboard computers advise the drivers, I think several other factors advise the drivers on how to drive that car to get the best life out of the battery packs.
Yeah, I've been trying to look for a BMS that you can set
Yeah.
at 4.0 volts, and they're all 4.2. It's like,
I think I might be able to pass on some programmable BMS links. They're a bit more expensive, but you can set them to what you want, which is nice. But anyway, video tutorials exist, so if you want to watch someone go through and solder and wire and make every connection into one of these custom battery packs, you can. OH8 STN directly for use with radios. You see here he's using lithium iron batteries, much larger lithium iron batteries here, which actually I would probably recommend this style. You see again, BMS, balancing connections, then out the other side just comes DC wires. So lastly, I have to promote this. If you're going to have your own mobile battery pack, the place to go use it. One of the cool things I've been doing and using mine with is parks on the air. Like Thunderbird is one of the parks you can go activate. Set up a mobile station, set up a simple dipole, be on the air and going. So it's really nice to set up mobile stations like we did last month here at OU. Took my capstone class out, we set up a mobile station, and actually on that afternoon, which was still bearable outside and warmth, we talked to Korea, Japan, they got a little bit into Europe, so these students got some nice exposure, and the battery pack's just one fraction of the mobile box you see contained down in here. That was all run off the little battery pack there in the back for about 2-3 hours, no issues. So that's what I've got. Thank you.